All right, my timer has begun, so I think even though it's right after lunch, and I'm sure a few people are still going to be trickling in, we are going to hop into things. So welcome to my talk, The Power of Function Composition. My name is Conor Hoekstra. I go by code_report online, so you might know me by that alias. This is the full About Me slide. I'm not going to spend too much time going through this because we've got a lot of stuff to get through in my talk. The stuff worth highlighting for the last 5 years, as you can probably tell by my t-shirt, I've worked at NVIDIA, which a lot of companies, hadn't heard of in the last couple of years. I guess everyone in tech has heard of it, but my parents finally know what company I work for, thanks to the stock price going up. For the 10 years that I've been in industry, I've been a professional C++ developer. Over the last 2 to 3 years, I've migrated a bit to Python, but I consider myself a polyglot programmer. So I've never checked any production .NET languages into production code, but I have written some C# and some F# for YouTube videos primarily. But I actually added some C# and F# code to this talk because I have heard from the first day of the conference that a lot of folks are working on the .NET stack. In the last 3 years now, 4 years, my favorite languages have become these languages that fit in this paradigm called array languages. If you've heard of APL, that is probably the most well-known of the array languages. Maybe if you include Julia, Julia is more well-known than APL. But APL was created in the 1960s, and then in the last decade, I guess J was created in 1990. But in the last decade, there's been a bunch of new languages inspired by these, and we'll talk about that a bit later. I have 4 different podcasts, so trying to compete with Richard Campbell, if you've seen any of his talks. The most well-known one is the one on the left there, Algorithms plus Data Structures equals Programs. We're approaching 200 episodes. It's a weekly podcast. Primarily, I'd say 70% of the podcasts focus on C++, but we jump around from language to language. Typically, it's more lower-level systems language. We just did a 5-episode series with Doug Greger, who's one of the top people at Apple working on the Swift language. We've also had folks to talk about the Rust language. If you've heard about the Carbon Initiative out of Google, we've also had Chandler Carruth, who's one of the top people working on that. So it's a programming language-focused podcast. Even if you're not a C++ person, you might be interested. The 2 middle ones are on array languages and related topics, and the last one's a running podcast. All of this stuff you can find on a GitHub repository called Content. My previous talks that I've given at other conferences. This is my first NDC conference, so happy to be here. It's been an awesome conference so far. But if you're interested in any of that stuff, check out this GitHub repo. So today we're going to talk about function composition. What is the goal of this talk? I'm sure if you're working in F# or a functional language, you've heard of function composition before. But I think function composition is a misunderstood thing in computer science. Most people think of function composition is composing 2 unary functions together. But that is just the tip of the iceberg. And my goal of this talk is to show you that there are different function composition strategies, there are different types of function composition, and hopefully at the end of this talk, regardless of what language you're working in, whether that's C#, F#, Python, JavaScript, any other language, that you can take some of these strategies and techniques and bring them back to your language. Maybe there's already a library that exists in your language of choice that you can just go and reach for. And if not, you can build these libraries. I've built a couple, and I'll mention them at the very end of the talk. So there are 5 different function composition strategies that I'm going to cover in today's talk. They are operators, functions, trains, chains, and stacks. Probably all of you are familiar with the first 2. Anyone can compose functions just by using functions. And if you've worked in a functional language like F# or Haskell, these come with operators that give you the ability to compose functions. And usually I save the goal of this talk or the summary of this talk till the end, but I'm gonna start to potentially confuse you, hopefully blow your minds by putting that slide at the beginning. So that is this slide here. These are the different operators and techniques for composing functions across the languages that we're going to look in this talk. And anything that's left white after I color code and highlight some of these are operators. But on top of that, we have functions, which are highlighted in blue. They only exist in Haskell. Then we have trains, which exist in the array languages. Then we have chains, which only exist in Jelly, which is a super, super esoteric language. It's actually designed for code golfing. If you've ever heard of the art of trying to solve a problem in as few characters as possible, Jelly was a language designed to be good at that. That is the sole purpose of the language. However, there are some very, very interesting programming language ideas inside of Jelly. Jelly is actually so confusing, though, that I had to write a tool to convert the Jelly code into something that was decipherable for me. And that's someone who understands everything to the left of the yellow bar. Like, I love APL, JCap, etc. And last but not least is Uiua, which is a stack language similar to Forth, Joy, Factor, if you've heard of any of those languages, combined with an array language. And so they don't necessarily have a strategy for composing functions, but you get a lot of this stuff for free when working with a stack language. So we're going to come back to this at the end. Probably most of you are just scratching your head being like, holy smokes, this is overwhelming. But hopefully by the end of this, some of this will make sense. Probably not all of it, I'll be honest, but hopefully some of it. So at the top left of this, we have FOF. Does anybody know? I made this term up, so you probably have never heard it before. But can anyone guess what FOF stands for? Someone actually came very close in another conference. No guesses? It stands for function-only functions. So it's a function that takes as arguments only functions and returns you a function. But in order to really understand that, we got to look at a bunch of terms. So these are the terms, these are combinators, and we're going to define that in a sec. And these are the terms that we're going to work through. Combinator, combinatory logic combinator, function-only function, pure function, and higher order function. We're going to go through this very fast because it's not entirely necessary to understand the rest of the talk. But if you want to come back to this after the fact and kind of digest this a bit more, I think it's helpful going down the road. So first, let's look at pure functions and combinators. So a pure function is a function that when you give it the same input, it always gives you the same output. No side effects. If you're used to F# or languages like Haskell, they refer to this as referential transparency. But basically, same input, same output. And they're very nice to work with. A combinator is a function that deals only in its arguments. It can't refer to anything else. No global state, no constants defined in the function. It only is allowed to deal in what you pass it. And when I first heard about combinators, my first thought was, are these the same thing as pure functions? They sound very similar. But they're not. You can come up with examples where you have a pure function, but it's not a combinator. For instance, if you have a function that defines a constant in the body of the function, that is not an argument that it's referring to. So that is still a pure function, because it doesn't refer to global state, doesn't have any side effects, but it's not a combinator because it's not dealing only in its arguments. So pure function, combinator, similar, but not the same. The next thought I had is, what's the similarity between these two and higher order functions? So a higher order function, if you're not familiar, is a function that either takes as an argument a function or returns you a function. Once again, though, you can come up with counterexamples where you have a higher order function that's not pure because it's got side effects, or you have a higher order function that's not a combinator. So these all are not the same thing. You can come up with examples that they all qualify for each of these, but they're not the same. My mental model, though, is that we live in a pure functional land, like Haskell per se, and we can assume that higher order functions and combinators are both pure functions. And so then the question becomes, what is a function-only function, and what is a combinatory logic combinator? Is it just this green circle? And the first answer to what is a combinatory logic combinator is no, it's not. There is this inner blue circle, which are the combinators from combinatory logic. And this is also referred to as the SKI combinator calculus, if you've ever heard those two terms before. This is basically a field of abstract mathematics that was created in the late 1920s up until the 1950s by a guy named Haskell Curry. The Haskell is from the language Haskell. Curry is from currying functions. I mean, both of those two things were named after that guy. It's pretty awesome if you can have both your first name and your last name used to name things. But there are combinators outside of combinatory logic combinators. If you've ever heard of parser combinators, that's something completely different. But that's because a combinator, all a combinator is it's a function that deals only in its arguments. It doesn't necessarily mean that it has to be a combinatory logic combinator. However, the K and I in the SKI actually aren't function-only functions. They are combinatory logic combinators, but K and I, which we're going to look at in a second, they don't necessarily need to take a function as an argument. And therefore, it doesn't qualify as a higher order function. So we have to put it outside the yellow circle. And then so finally, we're only missing the function-only functions, and that is the final pink circle. It's these combinators from combinatory logic combinators that only take as arguments functions and only return you a function. So it's a function that deals only in functions. You don't pass it any data, all your arguments have to be functions, and the return type has to be a function. And you might be thinking this is kind of confusing, but once we look at a couple examples, which we're going to look at in a sec, it'll hopefully start to make a lot of sense. So like I said, this isn't you don't need to actually understand this diagram, but it is helpful if at the end of the talk you think back to this sort of taxonomy or categorization. So we're done with this. And technically, this is more accurate. There is no such thing as a function-only function that's not a higher order function. So that yellow without the pink, really it should not be a circle. It should be whatever, we should get rid of that area. But, this is good enough. So let's, recap. Combinator, a function that deals only in its arguments. A combinatory logic combinator, that's just a combinator from combinatory logic. Function-only function, all its arguments are functions, and its return type is a function. Where you contrast that with a higher order function at the bottom, it has either or. It's either it takes a function as an argument or returns a function, and then a pure function, same input, same output. So, combinators. I've been talking all about combinators. You're probably thinking, what the heck is a combinator? Let's look at a couple. So, in the 1958 textbook written by Haskell Curry called Combinatory Logic, he defined the 5 elementary combinators and gave them pretty awesome names. The elementary identificator, the elementary permuter, the duplicator, the compositor, and the cancellator. So this is I, C, W, B, and K. And we're going to look at I first because it's the simplest. It's just a function that you return what it's given. The first time I saw this, I was like, what? That does absolutely nothing. How is this useful for anything? But then I also saw that in C++20, they actually added this, stood identity, and a lot of functional languages have this. Haskell calls it id. Clojure calls it identity. It is useful when you start trying to do these different composition techniques. So I just returns you what it's given. The next combinator, K, this is known as the cancellator because it discards the second argument. K is a binary function. It takes 2 arguments, and it gets rid of the second one. Once again, you might be thinking, why is this useful? But it comes in handy. Next up is, I think, the first interesting combinator, and it's the W combinator. So it takes as an argument f, which is a binary function, binary meaning it takes 2 arguments, and it basically turns that into a unary function, a function that takes 1 argument. And it does that by passing that single argument twice to the original binary function. So if you imagine f, we take a binary function, for example, as plus, adding numbers together. That takes 2 arguments. If you pass plus to the W combinator, that now becomes a function that you could call double because it's passing the same argument twice, so you're just doubling whatever number that's given. So here is, I believe, a small digression, which is that you're going to hear me use the words binary and unary, and then also sometimes I will interchange between monadic and dyadic. And this has nothing to do with monads. There are basically 2 different ways, Latin and Greek, to refer to the number of arguments a function takes. And these 2 things are called arity and adicity. And I think arity is the Latin one, and for 0 arguments, it's nullary, and then 1 is unary, 2 is binary, 3 is ternary, and 4 is quaternary. But then on the Greek side of things, they refer to arity as adicity, and then you have nilladic, monadic, dyadic, triadic, and tetradic. So this is a bit confusing because we got 2 different ways of referring to things. And actually, the very first time I started watching talks online, like years ago, in C++, they have functions in the algorithm header where they take, like, the argument is a template type, and it's called binary operation. And I was always confused because binary to me meant, 1s and 0s, binary arithmetic. I didn't realize it was referring to an operation that takes 2 arguments. So anyways, in case you're confused when I say binary, unary, monadic, dyadic, that's what this means. So moving along, this is the W combinator. So once again, f, a binary function that then W returns you a unary function. Very useful. Next combinator is B. So this is what most people think of as function composition. So B is a binary function that takes 2 arguments f and g that are both unary functions. And then it just composes them one after another. It applies g to your argument first, and then applies f after. So this is the dot in Haskell. And you can get this with the pipeline operator in F#, kind of. And this is what most people think of as function composition. Next up is C. This is known as flip in Haskell. I'm not sure if F# has this, but basically what it does is C is a unary function that takes a single argument, that is f, which is a binary function, and it just switches or swaps the order of the arguments that you're passing to it. So for an associative function like plus, this doesn't matter because it doesn't matter the order you pass it to. But for a non-associative function like minus, you have to sometimes the order that you pass, 10 minus 5, 5 minus 10 don't give you the same answer, whereas 10 plus 5, 5 plus 10 do. So this comes in super handy when you're dealing with binary operations. And last but not least of the elementary combinators is the S combinator. So this is where things start to get a little confusing. So S is a binary function that takes two function arguments, f and g. F is binary and g is unary. You apply g to your single argument x, and that gives you a result. And then you take that with your initial argument x, and you now have two things, g of x and x, and you pass that to your binary function s. So a little confusing, but this is actually extremely useful. And there's a reason that S is one of the 3 combinators in the SKI combinator calculus, because it's actually one of the most important ones. So I've gone through all of the elementary combinators, but there's a bunch more. And we're going to look at these via example, because honestly, I think that when you're showing these in a talk, it's a bit hard to show why these are useful in the abstract. It's easy for me to go through these and describe them, but like, what's the utility in these? Like, why are these useful? It's much easier to understand why these are useful when you look at an example. So, yeah, there's actually a couple extra off of this. I'll provide some links if you want to go look at them all, but these are the ones that we're going to talk about. So let's get to the example. This is kind of the most interesting part of the talk, and I think we're doing great on time. So this is an example from a LeetCode contest. I think it was like a month ago. It's called Special Array. And it's a pretty simple problem, but it's great for sort of solving these in different languages. And we're going to solve it in 10 languages. Originally, I solved it in 8, but I added F# and C# for the NDC crowd. So what is this problem? It is called Special Array 1. And it states you're given an array of integers, and it's considered special if every pair of adjacent elements contain 2 numbers with different parity. Parity meaning, is it even or is it odd? So basically, you want to have alternating numbers where it's odd, even, or even, odd. You don't ever want to have 2 consecutive elements that are both even or both odd. It's a pretty straightforward problem. And I think first we're going to look at a simple example, which we're going to use. So 4, 3, 1, 6, 4 numbers. The first thing we want to do is kind of group these by 2. So we've got 4, 3 are the first 2 adjacent, then 3, 1, then 1, 6. Then we want to check whether they're even or odd. So in array languages, you represent true and false by 1s and 0s. So 0 represents even here, 1 represents odd. And then we want to check, do none of these equal each other? So we want these to all not equal their sibling. And so for the first and the last one, they don't equal each other, but for the middle one, it does. So you're going to end up with 1, 0, 1, because the first and last are not equal, but the middle 2 are. And then we're just going to do like an all reduction because we want all of these to be true. We want all of these to be 1. But in this case, because we have a 0, your answer ends up being false or 0. So hopefully that makes sense. Now we're going to go through, initially, like I said, 8 different languages, but we've actually added, I've added F# and C#. I just did this a couple hours ago because I figured, we're at the NDC conference, why not? But first, we're going to start with Python. So Python only has functions when it comes to function composition. And first, we're just going to solve this, maybe how I would have solved this when I started learning Python in university like a decade ago, or a decade plus, I guess. So simple for loop, and we're creating a range of integers, 1 less than the length of our integer list nums. And then we're checking for each of our pairs, so nums I and nums I plus 1. Then we're doing modulus 2 to get the parity. And we want to check that if these are equal, we short circuit and return false. And if we make it to the end of our loop without ever returning false, you just return true. I really don't like this code, but like I said, this is how I probably would have solved it a decade plus ago when I was first learning how to program. So, any suggestions on something that we could do to simplify this? No suggestions? Well, the first thing I would do is get rid of the index. Having to index into these 2 things, I and I plus 1, I really don't like that. So you can make use of a function called zip in Python. And if we zip the initial list with the tail of the list, so the 1 colon in the brackets is basically a slice of our initial list, which drops the first element. So it starts your sub list or your slice at the second element, 1. And then this gives us a basically zipped pair of tuples, which are the adjacent elements next to each other. And so we can destructure those, x and y, and now I don't need to index into anything. So still not amazing, but nicer than what we had before. The next thing we can do is put this into a generator expression. So now because we don't have the indices, we can actually just put this destructuring for loop into a generator expression, and then instead of returning false and true, this is basically just a reduction all that's going to check to make sure that none of these are equal to each other. And note that we had to change our binary operation. Initially, we were checking if they were equal, then we were returning false. But now we are checking, we want all of them to be not equal. Technically, there's a function in Python called none, but I think it's easier to read that we want to see that all of them are not equal, that none of them are equal. But that's just kind of my personal preference. So at this point, this is where we're going to look at some C# and F# code. And I got to be honest, I did this a couple hours ago. You know, don't tell Richard, but I did it while I was in his talk. And I didn't want to write it myself, so I just went and asked ChatGPT. Technically, I think it's GPT 4.0. You get a couple of free questions. I managed to do this in like, a couple questions. So I just copy and pasted this code and said, GPT 4.0, could you convert this to C#? And this is what it gave me. Pretty ugly. Pretty worse than worse than this Python code. But that's there's one big change we can make here to make it nicer, and that's the following. We just move those braces over there. Now this is much nicer code in my opinion. Still not at all what I wanted. So like I said, I'm not a C# expert, but I know that if you want to do something in the functional style in C#, you reach for link. So I went back to GPT 4.0 and I said, thank you, this is very nice, but could you make it more functional and use link? And when it did that, it gave me the following, and this is much closer to what I was looking for. So you can see the zip that we had in Python. The 1: slicing that we were doing, you'd get with nums.skip1. It's basically dropping one element. And then when we zip nums with that sort of tail of nums, we then can apply some binary operation that's doing the modulus not equal to. And then we have this all function. A little bit irritating, but really this result, arrow result, that is the I combinator. If we had something where we could, in Haskell, it's just called ID, we could just pass ID right there. We just want a function that returns you what it's passed, because when we perform the zip, we're going to end up with a list of trues and falses. And clearly what the link all function does is it checks for some condition, do all of these satisfy the predicate. But we already have a list of trues and falses. We don't need to apply a predicate. We just need to apply the identity function. So this is pretty nice. I think that's the extent of the C# code. But then I asked it, great, can you do it for F#? And it nailed F# on the first try, because there is no imperative looping solutions in F#. It's a functional language. And pairwise does the zipping for you. Nice that we have a built-in function. So that zip tail trick, that's just called pairwise in F#. And then we just do this array for all, very similar to what we had in the link code, and pretty nice. So ndc.net, we got some F# and some C# in the slide deck. Back to the Python code. So now we have this generator expression with a zip, we're destructuring. But when I see this code, I think to myself, that's a combinator. Because what we have here is not equal. That's a binary operation that takes 2 arguments. And we're applying that binary operation after applying the same unary operation to 2 different arguments, the modulus 2. And so we can convert this to use something called the psi combinator, where we apply a unary operation to 2 arguments first, and then take the results of those and pass them along to a binary function. So in operator module, they have a not equal function that is ne. And then in this dovkey library that I've written that provides you a bunch of these combinators, we've got odd, which is a unary function, and then psi, which is a psi combinator. So the psi combinator, to be explicit here, is a binary function that takes 2 function arguments, f and g. G is unary, and f is binary. You apply g to 2 different arguments, in this case odd, and then once you have the result of that, you pass the 2 results to the binary function f. And by using this psi function, we can get back to this code. So this, I think, is actually worse than the previous solution, but that's because we're destructuring the x and y and then passing it to the function we formed by passing not equal and odd to psi. But we don't actually need to do this. The map in Python is very attic, so we can get rid of the x and y and the destructuring and just replace this with a map that's mapping over two lists, the nums and the nums1 colon, the pairwise that we had from F#, and then we can just pass this function that's returned by psi. And this, I think, is actually quite nice if you compare it to where we started it with the for loop returning true, returning false. So this is Python. We're going to come back to Python at the end, but I think we're going to move on now to Haskell. And Haskell's Haskell. I mean, I love Haskell. At one point, it was my favorite language, but it's a bit confusing, and you're going to see why. So this is the equivalent of the code that we just saw in Python. So map odd. That makes sense. You're just mapping odd over your list of integers. Fold1 ampersand ampersand. That's just the equivalent of our all in Python, or our for all in F#. But what is this zip width not equal to angle star angle tail? So if we go back, and also make note of the two dots, if we go back to our little combinator table and we look at the Haskell column at the very end, the dot is the B combinator. And the angle star angle is the S combinator. So remember that function, that combinator S that takes a binary function and a unary function? And I said, oh, it's kind of confusing, but it comes in useful. Well, we're using it right here. So if we come back and we just focus on the zip width not equal to angle star angle tail, that's the S combinator. So tail is our unary function, and zip width not equal to is our binary function. And so basically, this is a way of spelling what pairwise did in F#. It's zipping the initial list with its tail, and then it's going to apply a binary operation. The operation that we're applying here is the not equal to. That's that slash equals. For some reason, Haskell spells their not equal to different from every other language. Although, so does F#. If we want to be, F# uses, angle, angle. It's upsetting when there is disagreement across languages on operators. We all agreed on what plus was, but when it comes to exponents, not equal to, every language had a different decision. So that's basically what zip width not equal to S combinator tail's doing. However, even though it's cool that you can spell it this way, we can avoid this by making use of a function similar to pairwise that we had in F#, but it's slightly different. Pairwise just does the zipping action for us, but map adjacent here, it bundles a binary operation with it and then applies that binary operation to the zipped elements at the same time. And in my opinion, this is actually really, really nice code. Like the zip width not equal to S combinator tail, I think that's elegant, but it's hard to parse. This, however, is much easier to parse. We're mapping odd, mapping adjacent elements, applying not equal to, and doing fold1 ampersand ampersand. And luckily, the fold1 ampersand ampersand, we actually have a nicer way to spell this in Haskell, and that's and, which I think is unfortunate because this is the equivalent of all in Python, but for some reason they decided to call it and in Haskell. And all is a different function. So all does exist, but it does something different. And yes, so this is our final Haskell solution, except it's not. We used the psi combinator before in the Python code. Can we use the psi combinator here? We're mapping a unary function odd, and then we're mapping adjacent a binary function not equal to. That's the psi combinator. And in Haskell, they call the psi combinator on. So we can actually compose these two things, which is saying take two elements, adjacent elements at a time, and first apply odd to each of your adjacent elements, and then apply your binary operation. And in my opinion, this is extremely elegant code. Still a little bit hard to read if you're not familiar with Haskell, but compared to what we started with, the zip tail with the S combinator, this is really nice. So I think up next we have, we're going to revisit. So what if we had the map adjacent in Python? So this is where we ended with the Python code. But if we make a little room, add a map adjacent, how does this change? Well, we get rid of our map, replace that with a map adjacent, and then we can get rid of the nums and the nums bracket 1 colon and just pass nums once. And now once again, I think this is more readable code. You still have to have access to this, and unfortunately, Python does not have a adjacent map in a library anywhere. But still pretty easy to write. And note that pairwise is the exact function that we had in F#. You have to find this in a library called itertools, but it exists. It just zips with your basically sibling, your adjacent elements, two at a time. So I think at this point, and I think, the point that I'm making here is we don't even need to use the psi combinator at this point because adjacent map takes a binary operation. We're forming a binary operation here, but if you wanted to, this might be more idiomatic in Python code. Just use a map your odd over nums, and then pass that as the first argument to adjacent map, and then the binary operation you pass to adjacent map is the not equal to. So once again, we're going to come back to Python, but we're going to keep moving. So Clojure. Here, we have functions and operators. We already looked at F#, so we're going to go through this really quickly. This basically is something called the thread last macro. It's also referred to as a thrush operator. It's similar to what the pipeline operator or the pipe forward operator in F# does. It basically just passes your argument along to the next operation. In this case, it's passing it as the last argument to each of your operations. So partition does your kind of creating a list of two adjacent elements. The map is performing the not equals to, and then the every at the bottom is the equivalent of the all in C#. Once again, it wants a predicate in order to check, do all of my elements in my list satisfy this predicate? But at this point, we have trues and falses, so once again, we can use the I combinator. In this case, we actually have the I combinator in Clojure, and it's called identity. Here's an alternative Clojure solution where it's just basically combining the last two into one and using a slightly different syntax. This way, we can avoid using the I combinator if we want. It's your preference which you like more, but anyways. Clojure, similar to F# in some regards. And with that, we are now going to move on to my favorite part of the talk, which is all of the array languages. So APL, BQN, J, and cap. And all of these languages have operators, but they also have trains. Technically, you could write functions if you wanted to do function composition, but that's not the idiomatic way to use these languages. So first things first, trains, what are trains? Trains are basically just the juxtaposition, they putting side by side of functions. So when you put two functions next to each other in APL, that forms a two train. And when you put three functions next to each other, that forms a three train. And you can continuously do this so that when you form a three train, that'll then form a function, which is probably going to be unary, or at least it will be in the cases we look at. And then we can continue to build up these longer trains, which we'll see when we do this by example. So J was the first array language to add these trains, and they did it in 1990. And for the two trains, they chose S and D. And for the three trains, they chose phi and phi1. At a certain point in 2014, Dialog APL, they're the sort of main company that implements an APL these days, they decided to add trains because J did, but they switched the S and D to the B and B1 because they realized that those were better choices for reasons I'm not going to get into. And then since then, cap and BQN have made the same decision. Note, though, that cap did not add the three train, which is incredibly interesting. It is opaque now, but once we get to the live coding, you will see why it makes a difference. If we look at these for the ones that correspond to the two trains and three trains, we can hide them. We've got S, B, D, B1, and phi. And if we get rid of S and D and add phi1, in the modern APLs, sort of excluding J, this is what we have. So the first two, B and B1, are the two trains, and then phi and phi1 are the three trains. So B we've already looked at. B1 is just basically an extension of B, where instead of applying a unary operation after a unary operation, you're applying a unary operation after a binary operation. Super useful. And then phi and phi1, these get a little bit more confusing, but we're going to see them in examples and they'll make more sense. But basically, phi, you have a binary function and two unary functions. So it's similar to psi, where we applied a unary operation to two different arguments, and then the binary operation afterwards. Phi, it has two different unary operations and applies them to the same argument. Then you have two results, and you pass those along to the binary operation. And the phi1 has the same pattern, but instead of applying it to a single argument, it applies the f and h to two arguments. So I believe this brings us to the live coding portion of this talk. Hopefully the internet's working, because this is all going to be done in the browser. So everything you see now, you guys can go and try later after the talk, or if you want to whip out your laptop right now. You could technically even do this on your cell phone, because you can just go tap those symbols, and the solutions are so short, as you're about to see. It's actually not that hard. You know, you don't want to go code C# on your cell phone, but for array languages, it's actually possible. So this is tryapl.org, and this is how you create a list. Maybe I should make this no, we'll keep it at this size because that was terrible. This is a list of 4 numbers, so that's what we're going to work with. The first thing we want to do is we want to check if these are even or odd. So this 2 pipe is how you do 2 modulus. So the %2 in Python, you spell by 2 pipe, and we do this, it's basically going to return 0 if it's even and 1 if it's odd. So 2 characters, we're like halfway there. Next thing we want to do is we want to take 2 adjacent elements at a time. So there's an operation in APL called an n-wise reduction, where you specify n, the number of elements you want to look at a time, and then it creates you sublists of that length n, and then creates like a sliding window. So if we want a adjacent elements, we can basically do 2 catenate, which will form you a list, and then the reduce is the slash. And so when we hit this, it's going to give us basically the first 2 elements, then it's going to slide by 1, give you the next 2 elements, and then slide by 1 and give you the last 2 elements. But what's amazing about this n-wise reduction is you can replace this operation with any binary operation you want. So in our case, we want not equal to, so we just replace this with a not equal to, hit enter, and I have to delete the catenate in order for that to work. And then we get our 101. And you can do this with any binary operation. So if we were solving a different problem and we wanted to put a plus there, if we wanted to put a divides there, a domain error because you can't divide by 0. If we did this, though, it would work. Anyways, pretty cool. So let's go back to our not equals and 2 modulus. We got to type the 2 modulus. And so after this, all we want to do is an and reduction, which is just 2 characters. That's and as we saw before, this is reduce. And that is our full solution there. Pretty fantastic. We all want to switch to APL, right? So now let's switch over to the other APL, CAP. And so this is basically an APL-inspired language, but it makes a few different decisions. The main one here is that they don't have a 3 train. And actually, let's quickly back, because we didn't actually solve this tacitly. So here we've built up just an expression that's going to evaluate eagerly. Oh, the screen disappeared. All right, don't touch the computer too hard. If we try to evaluate this, though, it doesn't start with a 3 train, so we're going to get a syntax error. So in order to get this to evaluate correctly, we need to add an identity here. So what this is going to do is then this is going to correctly form us a 3 train, which is going to be the phi. This will form another 3 train, and then this will be our final 2 train, which is a B combinator. So this will parse. Actually, if we type this correctly. So this will parse correctly, but keep this in mind. We had to make this slight change in order to get this to work. So let's do this a lot quicker for CAP. So we've already seen this. 4316 is our initial list. Then we want to do even or odd. That's 2 modulus. Then we want to do our n-wise reduction. So here we're going to do catenate once again just to show the 2 pairs that are forming. And then we're going to replace that with the not equal to get our 1s and 0s. And then last but not least, we're going to do our and reduction. If I can type this properly. So same thing we just saw, but in this case, we don't have the 3 train. So what's going to happen when I parenthesize this to turn it into a point-free tacit expression is that this is going to form a unary function because of something called left-bound functions. This is going to form a unary function because of something called left-bound functions. And this is already a unary function. So we just have 3 unary functions next to each other, which is just going to be 2 B combinators after each other. So when we evaluate this, we get the same result, which this is really, really nice because in Dialog APL, we had to make a change in order to actually form a point-free function, whereas in CAP, we don't need to do that. All right, switching back here, we're going to go to BQN. So BQN is a modern APL that has slightly different glyphs. It was actually supposed to be APL plus 1 for each of the characters. A plus 1 is B, P plus 1 is Q. But then they messed up the N, because L plus 1 is M, not N. So it's actually, the joke is now that BQN is APL plus Fibonacci, if you're familiar with that sequence. Anyways, this is similar. So we've got 2 modulus, and that gives us, so we've got 2 different test cases, one that's going to pass and one that's going to fail. And unfortunately, we don't have the n-wise reduction in BQN. So the thing we have to do here is we have to use a function here called windows, and that basically turns it's similar to the m-wise reduction, but it gives you a matrix of 2 elements at a time. And you can do this for the same thing, like 2, 3, 4. And after this, we want to do a basically not equal to reduction over. So let's see if we can type this correctly. Actually, let's do it this way. Not equal. For some reason, this is where is not equal? No, this is not. Let's see if we can copy it from over here. There we go. Not equal. And then we need to do this with cells. So that should give us what we're looking for. And now we want to do our AND reduction. Unfortunately, this isn't going to work now. So this should give us our right answer. But what we have here is a 3 train, followed by another 3 train, followed by a unary function, which is going to be the B combinator. And you can't have 2 unary functions in a row. So you have to do this trick, which is add this thing called nothing, which basically it breaks after your single unary function and then enables you to call another unary function and still form the B combinator. So a little bit unfortunate that we have to do that. And last but not least is J. So J is an array language. It was Ken Iverson's second array language. He did APL in the 1960s, and then he did J in the 1990s. And it was basically just APL, but using ASCII symbols. So you can type it without all the special characters. So once again, 4316 is our list of numbers. Then we can do 2 modulus. So the pipe actually exists on our keyboard, so that stays the same. And then you get our list of 1s and 0s. Then we can do our n-wise reduction. Oh, it's pretty flaky. Oh, we're back. We can do our n-wise reduction as so. So this is the equivalent of our catenate. But if we change this to not equals to, which so not equals to does not exist on your keyboard. So you spell that with a squiggle colon. And then you have to put that with a reduction. So that gives us our 1s and 0s. And then you want to do an AND reduction. Once again, the AND doesn't exist on our keyboard, so you spell that with an ampersand or asterisk dot and then slash for the reduction, which is going to work once again. So in order to make this point free, we have to put this thing called cap, and then we'll space this out so it's a little bit more legible. And, if we do this, then we are able to parse correctly because we have a 3 train followed by another 3 train followed by a unary function, but because they chose the 2 train to be the S combinator, we don't want the S combinator right now. We want the B combinator. So you have to use the cap in order to turn the S into the B, which we're going to talk about a little bit later. So that got us through the first portion of our LIDE coding. The next language that we're going to look at is Jelly. So Jelly, like I said, was a language designed to be a code golfing language. And it doesn't have trains. It has something that is called chains, which is similar to this idea of trains that you put functions next to each other, and then it forms some kind of composition pattern. But the way that they do it is they don't hard code, 3 trains as phi and phi1 and 2 trains as b and b1. They basically just have a pattern matching table, a list of look at the arities of your function. If you have 2, 1, 1, that's the D2 combinator. If you have 1, 2, 1, that's the phi combinator. So you just, and one of the reasons it's able to do this is that in APL, BQN, CAP, and J, all of their functions are ambivalent, which means that they have 2 definitions. The easiest one to think about is the minus sign. Minus is subtraction in the dyadic case where you have 2 arguments, and it's negation in the case where you only have a single argument. But they took that, that exists in mathematics for the minus operation, and they did that for every symbol. So, maximum is both maximum when you're given it 2 numbers, and it's ceiling to go to the closest integer, or the rounding up when you have a single integer. And so because of this ambivalence, every function has both a unary definition and a binary definition, which means you can only do so much in terms of pattern matching. Whereas Jelly, every function is fixed. Its arity is fixed. So you're able to do more. So we're going to look at this example. It's easier if I don't live code this and then just show this one by one. So we've got a simple example, 416. If we want to check are these odds, this is the Jello tool. So the Jelly is the yellow B overdot. But that means nothing to me. And so Jello is a tool that I wrote that basically I can type in keywords and it does the conversion behind the scenes to the Jelly interpreter. So odd is odd question mark. That's my Jello keyword that I've added. But the actual Jelly is the yellow code. So now we've got our list of 0s and 1s for odd. We want to check are the adjacent elements not equal to each other. And we do that. We actually have a built-in function in Jelly that I've called differ, which basically checks to see are the adjacent elements different from each other. And in Jelly, this is a D accent caron. Because that's how they get away with, I think the person that made this is Spanish, and so they've got all these underdots, overdots, accents, and that's how they spelled their language. Yes, I saw someone put their hands up like, what are we doing? Remember, the goal of this language was to code golf. It's not to be readable. In fact, they added something that actually like compresses these symbols. Like if it has a string, it can compress it into absolute nonsense, but like save bytes of code. Anyways, it's if you think this is bad, you should see some of the other parts of the language. And last but not least, we want to just do an all reduction, which we call all here. And so that is our final solution in Jelly, the B overdot, D accent caron, A underdot, 3 letters. But what's interesting about this is that where is the function composition? Well, the pattern matching engine in this case says whenever we have a series of unary functions where the arity is 1, 1, 1, 1, 1, you just continue to apply the B combinator. You just apply the function after the last function was applied. And so I have a tool here that actually shows you, this is a super simple arity chain, where your arity chain is just 1, 1, 1. But this shows you that it's the B combinator, and then after that it's the B combinator. But this will do it for all different types of combinators, the S combinator, phi 1, etc. So very cool tool if you want to go play. And this idea of function composition by chains, just look at the pattern matching of the arity chains that are formed by the juxtaposition of your functions is a really, really interesting idea. So this is, because I built this tool, I built a bunch of stuff into it. So you've noticed that across these solutions, when we were in Haskell, we started with fold L1, ampersand, ampersand. But you can actually spell and. You can do this in Jello just by basically typing whatever you think, and anytime it notices that you could use a different algorithm, so differ, for instance, you could spell that with a not equal to prior. Prior is what they call map adjacent or what I call map adjacent in Jello. But if you type that, the algorithm advisor will just say, hey, just use differ here. Or if you use an and fold to do an all reduction, it'll say, hey, you can just use all instead of that. And you can note at the bottom too, one of the reasons I showed this is it just shows you that you can see a different arity chain here. You've got 1, 2, Q, 2, Q. All right, I think this brings us to our last language that we're going to look at, which is Uiua. And so this uses operators plus stacks. So like I said, stacks kind of had an asterisk before because this isn't actually corresponding to the S combinator, the B combinator, but you get a lot of this stuff for free. So let's hop back to our browser, go to the Uiua tab. And so once again, this is just another online editor that you can use, and we're going to build this up. So the first thing we're going to do is, once again, our modulus 2. So one of the interesting things, if I can type this correctly, is that all the other languages I had to memorize keyboard shortcuts, and I just code in these languages enough that I kind of know them all, except for the case of BQN when I couldn't type the not equal to symbol. But here, we just type the start of the name of our function that we want. So here we want modulus, and as soon as the prefix of that function that you want turns a certain color, this turned blue, you can then just hit Control-Enter, and it converts that prefix string, the name of your symbol, into the symbol. So I actually don't need to memorize any of these keyboard shortcuts. And because of that, this language has actually gotten, in the array language space, quite popular quite quickly. This was only released in September of 2023. And anyway, so that's how you do 2 modulus. Once again, we don't have the n-wise reduction in Uiua. We have to do the Windows trick. So if we do win for Windows 2, this is going to give a matrix where each row is 2 elements at a time, and then you move one by one. And then we want to do our not equal to reduction here. So we're going to do rows slash and then not equal to, hit Control-Enter. It's going to turn these all into symbols. And then this does our sort of not equal to reductions across each of our rows. And then last but not least, we're going to do our all reduction, which you spell in Uiua slash and then min, and then we're done. But once again, similar to the jelly code, it's not apparent if there's any composition here. And there's not really. You can think of some of this as just kind of unary function composition, but the way that stack languages works are they just apply whatever function is at the top of the stack to the arguments that are on the argument stack. And anyways, it's food for thought because this is, this Uiua language was inspired by BQN, but it gets a lot of the same functionality without actually having to reach for these combinators, which might be a good thing. So that is the Uiua code, and that brings us to the summary of these 6 languages. And I sort of want to go through, once again, these different train models, chain models, stack models. So in the cap code at the top, we start off by forming a unary function. So this is just something in cap. Whenever you have a binary function with an argument on the left, that's called a left-bound function, and that just forms your unary function. And we get the same thing with the 2 not equal to slash, the 2i's reduction. And so we have a unary function followed by a unary function. And this is just the B combinator. And then the and reduction, or just all, that's another unary function. So this is just the B combinator. So 2 B combinators, because we have 3 unary functions in a row. And this is made possible by the fact that there's no 3 train. Whenever you have a 3 train, that and would then want to interpret that the 2 equals 2 as a 3 train, and it's not going to work. So, or you need to put like the identity at the beginning, which then forms a 3 train, another 3 train, and then a B combinator, which is what you have to do with dialog APL. So this, I think, is actually a nicer model than the dialog APL one. In the second example, we start off with a 3 train. So that's the phi combinator. And then that forms a unary function, which with the 2 not equal to slash forms another 3 train, the phi combinator. And then the and reduction is a unary function, so that's the B combinator. So this is almost identical to the cap code, but it's a lot more confusing, in my opinion, to understand. And that's because it has 3 trains. Uiua we just covered, and as I mentioned, like unary function, or it's technically the application of a partially applied binary function, which is a unary function, but you know, potato, potato. No one says potato, but and Windows 2, once again, another partially applied binary function, and then this is a unary function applied. This is a unary function applied, but like we don't need to use any combinators to get this kind of composition for free. So it's interesting. And note that because we've got the blue here, we need that because there's no n-wise reduction. So one of the points of this talk too is the algorithms that you're able to reach for and use affect the combinators that you need to use. BQN, similar to dialog APL, we start off with a 3 train, which is a phi combinator, then another 3 train, which is the phi combinator. But in this case, because once again, we don't have the n-wise reduction, we need to reach for the not equals to row-wise reduction, but that's a unary function, so this is a B combinator. But now, because we have a B combinator, you can never get 2 B combinators in a row without using something to disambiguate. So we have to put a B combinator here, but that nothing, we got this little devil emoji. This, in my opinion, I'm glad that BQN has it. It's just unfortunate that BQN has to have it in the times when you want to do stuff like this. The J code, 3 train, phi combinator, 3 train, phi combinator, 2 train, B combinator. But once again, we have to use this cap thing for a different reason than in BQN. BQN, we needed it because we had 2 B combinators in a row. In J, we needed it because the 2 train is not the B combinator. It's the S combinator. And so they have this thing called cap, which turns a 2 train from being S to B, which this is extremely confusing in my opinion. The fact that you have a special token to change the meaning of a train. Trains already are confusing, but the fact that you have a token that can change the 2 train from an S to a B, and I also think it's incredibly hard to read. I mean, most of you are probably thinking all of this is incredibly hard to read. But I think the fact that J uses multiple ASCII symbols, at least the other languages, they use single symbols to represent functions. But here you need to know that the asterisk dot, that represents and. You need to memorize basically when symbols end, which is, it's just extra things to learn. And then last but not least, the only language that reads left to right of these 6 is Jelly and Jello. So odd, unary function, differ, unary function, B combinator, all, unary function, B combinator. So similar to cap, just the opposite direction. And obviously the thing you can note about the Jello code is that this semantically it's identical to, other than the Uiua and BQN solutions, it's identical to what the other code is doing. But it's incredibly readable and really, really nice in my opinion. So this is a summary of across all the languages that we've looked at, which ones have access to which function composition strategies. And I think that brings us to the sort of conclusion of our talk, which is, look at that, doing great for time. I think this code is incredibly beautiful. However, beautiful code is a subjective thing. One person can look at the initial Python code and they say, oh, I prefer for loops and if statements. I think that's the most beautiful readable code because I don't need to learn anything extra. I don't need to go learn what's in the itertools library. Some C# developers would say that their code is more beautiful than the F# because of the same reason. I can understand for loops and if statements. I love this code. It speaks to me, but it is the essence of what I'm after. A lot of other languages require a bunch of ceremony, whereas these do not. And a lot of that is because of the function composition strategies that you have access to in these languages. One of my podcasts, it has the title Algorithms plus Data Structures equals Programs. This is a Nicholas Wirth book that was written. It's actually taught, the book teaches in Pascal. But in array languages, there's really only one data structure, and that's the array. There's no hash maps, there's no sets, it's just the arrays, and you can represent sort of the different data structures using this. So I'm starting to, my opinion of the title of this book, it's really scratch out the data structures and replace that with combinators, and scratch out the programs and replace that with beautiful code. And so the question is if you're in a language that has access to different data structures, what if you add the combinators, though? You can get even more elegant code, in my opinion. Like I said, we started off with this. Hopefully, you understand a little bit more of this. But the point is on your free time, if you want, go and check these out. Not because I want you to switch to programming in APL, but take these, compositions other than just the B combinator and see how you can fold those into your language. We've been coming back to the Python solution over and over again. We left it at this adjacent map, which we borrowed from Haskell. But what if we borrowed the differ, which was in Jelly? What do we end up with? We no longer have any combinators here, which is what I mentioned earlier. The algorithms that you have at your disposal, the things that you can reach for in libraries, affect the code that you can write. And a lot of the discovery of these types of algorithms come from my exploration of these languages and learning about the combination or the composition strategies. And if you look at this compared to what we had in the very beginning, I found it very hard to for anyone to argue that this isn't a simpler, more elegant. Sure, I need to know what differ means, but that's basically the only thing here that's not in your basic, idiomatic Python. Everyone in Python knows what a map is. They know what all is. I guess odd, but I think everyone knows what odd means technically. So be curious. Go and try and learn these languages. And on top of this, you might be thinking, why is a person from NVIDIA giving this talk? I do it because I'm really interested in these array languages. But differ and map, they're both maps. Differ is just an adjacent map, which can be implemented using a map. All, that's just a reduction. Reductions and maps, map reduce, heard of that? GPUs eat this stuff for breakfast. The for loop that we had in Python originally, it's hard to accelerate that kind of code. You can do it, but it's so much easier to accelerate this kind of code. And that's why CuPy exists. It's a CUDA accelerated NumPy, because NumPy is just a bunch of operations. And if you can go accelerate all these operations, it's so much easier to basically get accelerated code. So the point being is that there is actually some utility other than just, oh, look, I can write my code a lot shorter by having access to this different stuff. You can implement this stuff a lot faster at the end of the day. So last but not least, if you want to go try these languages out, as I mentioned, all of that stuff was in the browser. You can find this, the same content GitHub repository where I listed all my talks and podcasts. You can find the slide deck and links to all of this stuff if you want to go check this stuff out. If you don't want to go check that out and you are in one of these two languages, I have two different libraries that basically implement a lot of these combinators. I use them basically in all of my personal projects because whenever I have to write a Lambda that's doing some simple thing, a lot of the times there's a combinator for that. And with that, I will say head over to combinatorylogic.com to learn more, and thank you for your time. I'll be around for the rest of the conference if folks want to come and talk to me, because yeah.